95% of the land in Saudi Arabia is occupied by harsh desert, where natural rainfall is almost non-existent. Why would a nation build a massive steel water delivery system spanning thousands of kilometers across such an arid landscape? One might assume that groundwater or rare oases could sustain the population, but in reality, the scale of modern demand requires an engineering solution of unprecedented proportions to draw life from the Red Sea. It only looks obvious to rely on local wells, but the sheer volume of consumption has forced the creation of a massive industrial infrastructure. Billions of liters of seawater are drawn into enormous desalination complexes every 24 hours to begin their transformation. This process is only gaining momentum. Large-scale intake systems pull the water into treatment facilities where salt and minerals are separated to create fresh water suitable for drinking, agriculture, and heavy industry. One can notice how the equipment gradually processes the brine, preparing the liquid for its long journey into the interior of the country. The engineering feat does not end at this stage. Pumping stations drive the water through a pipeline network that stretches across thousands of kilometers of shifting sand and rock. Huge steel pipes, manufactured to withstand extreme internal pressure and external heat, form an invisible river that sustains the entire nation. The camera glides along the segments of these conduits, which are buried or reinforced to survive the desert environment. At first glance, the system appears to be a static network of pipes, but in reality, it is a dynamic and constantly monitored technological achievement. Everything only gets more complicated when considering the energy required to move millions of tons of water uphill from sea level to high-altitude cities. Automated control centers regulate the flow with millisecond precision to ensure that not a single liter is lost to the heat. Because the survival of millions depends on this infrastructure, the maintenance of the steel arteries is conducted without a single day of interruption. It is visible how the massive pumps vibrate with the force of thousands of horsepower, pushing the fresh water toward its final destination. This marks the successful completion of the primary delivery phase, ensuring the desert remains inhabited and productive. 37 million people inhabit the sovereign territory of Saudi Arabia, and almost every individual within this population adheres to the faith of Islam. Why is the demographic distribution of this nation so drastically uneven across its geography? It would seem logical for a population to spread across available land, but in reality, the vast majority of citizens are densely concentrated along the narrow corridors of the Red Sea coast and the Persian Gulf. The interior of the country remains a nearly uninhabited desert, where the horizon is broken only by shifting dunes. At first glance, the land appears to have everything a modern economy requires, as it possesses 40 trillion liters of oil stored deep beneath its soil. But this abundance is countered by a fundamental biological deficit that costs the state billions of dollars to manage. Nature does not provide every resource in equal measure to this region. The average annual rainfall remains below 100 millimeters, while summer temperatures regularly exceed 45 degrees Celsius. To survive under these extreme thermal conditions, Saudi Arabia engineered a nationwide water pipeline system. One can notice how the network utilizes high-strength carbon steel pipes, which are technical twins to those found in the global oil and gas industry. Construction costs are significant. They average $3 million for every single kilometer of pipeline laid into the earth. It gets more complex further on. This figure does not include the essential booster pumping stations or the advanced desalination plants, each of which requires an investment of tens of millions of dollars to become operational. Where does this massive pipeline network find the liquid required to sustain millions of lives? The engineers turn to the nearly inexhaustible volume of the sea. However, seawater contains approximately 3.5% salt, making it far too saline for human consumption or agricultural irrigation. This physical barrier led to the development of sophisticated desalination technology. Desalination gives Saudi Arabia a nearly unlimited supply of usable water. The pipeline carries this treated liquid from giant desalination plants situated directly on the shores of the Red Sea. The process is only gaining momentum. On a daily basis, a single plant of this scale can convert 7 million liters of seawater into drinking water. The equipment gradually processes the intake while consuming a massive amount of electrical energy to separate the salt from the fresh stream. The desalinated water moves through the carbon steel arteries toward the distant cities. From here, the transformation moves to the next phase of distribution across the desert landscape. 1,800 millimeters is the diameter of the high-strength carbon steel pipes that form the foundation of a transnational water pipeline. Why is this specific material selected for such a massive infrastructure project? The alloy is nearly identical to the steel used in high-pressure oil and gas networks, providing the necessary resilience to endure continuous pumping force and mechanical impacts during underground burial. Furthermore, it must withstand the relentless thermal expansion and contraction cycles common in extreme desert environments. One can notice how rectangular steel plates are first cut to pre-calculated dimensions with high-precision shears. The process is only gaining momentum. These massive plates, featuring a wall thickness of nearly 25 millimeters, are fed into a heavy-duty multi-axis rolling machine. One can notice how the rollers exert immense pressure, gradually bending the rigid steel step by step in a controlled arc. The movement continues until the two longitudinal edges meet with precision, forming a hollow pipe blank that is ready for the critical stage of longitudinal welding. It seems simple to join these edges, but in reality, the structural integrity of the entire pipeline depends on the quality of this seam. Once the longitudinal welding is completed, the pipe is immediately passed through a straight-flow water cooling line. The equipment gradually lowers the temperature of the weld seam with a continuous spray, preventing thermal distortion of the metal structure. The pipe sections then move toward the grinding station. Skilled operators and automated systems carefully grind all edges and corners to remove metallic burrs and ensure absolute geometric accuracy. It is visible how the metal surface becomes smooth before the next welding phase. This preparation is vital for the finishing of both ends with beveled edge welds. These precise bevels create optimal contact surfaces, ensuring that joint connections will be seamless during field assembly. 12 meters is the standard length of each individual pipe section produced at the facility. But this is just the beginning. This specific length is a calculated compromise that reduces the total number of welds required across hundreds of kilometers, while remaining practical for logistics. Such a design allows the segments to be joined quickly, maintaining pressure-tight seals and long-term structural stability once installed along the cross-country route. The equipment gradually moves the completed steel pipes to an expansive outdoor storage yard. Here, the sections are stacked by batches and clearly marked with unique identifiers for logistics and digital tracking. At first glance, the yard is a simple transit point, but in reality, it is a highly organized hub for the entire project. One can notice how heavy-duty forklifts or overhead cranes lift the pipes onto specialized transport vehicles with deliberate, slow movements. The pipes are securely fastened to the trailers using heavy-duty straps to prevent any deformation or shifting during the long journey. Everything only gets more complicated as the convoy begins its transit. The pipe sections are hauled hundreds of kilometers across rugged terrain to reach the remote construction site. Upon arrival, the segments are positioned end to end and welded together directly along the pipeline route to form a continuous conduit. The material leaves the factory, transitioning into a calm stage of final assembly in the field. 40 meters is the exact width of the construction corridor cleared in advance to facilitate the continuous movement of heavy machinery across the desert. Why must such a vast area be prepared before a single pipe is even moved? This expansive space allows the entire installation sequence to proceed at a relentless average pace of 1.5 kilometers every 24 hours. At first glance, the desert floor appears ready for construction, but in reality, specialized preparation is required to prevent shifting sands from stalling the workflow. Engineering teams initiate the process at massive staging yards positioned strategically along the planned route of the pipeline. One can notice how fully manufactured steel pipe sections are grouped with mechanical precision according to their specific diameter, length, and intended installation sequence. Technicians perform final visual inspections, scrutinizing the straightness of each pipe, the integrity of the external coating, and the accuracy of identification markings. This stage is not merely organizational. It is a fundamental necessity for maintaining a continuous workflow and reducing human error while operating under harsh environmental conditions. The process is only gaining momentum. Survey teams simultaneously establish the precise trajectory of the pipeline across the barren landscape. Using global positioning systems, total stations, and detailed terrain data, they mark the alignment directly onto the desert floor using wooden stakes and high-visibility paint. This ensures the steel conduit follows the most stable and efficient path possible. It is visible how the route avoids zones of weak soil, shifting dunes, and areas prone to rapid erosion. For systems stretching over hundreds of kilometers, this accurate routing is the primary factor in long-term structural integrity. Construction sites must be cleared and leveled to a high degree of flatness before any trenching begins. Temporary access roads are opened parallel to the main alignment to accommodate the constant flow of trucks, excavators, automated welders, and material transport vehicles. In the desert, this preparation also involves intensive dust control and sand stabilization measures to maintain visibility for operators. Everything only gets more complicated as the heavy equipment arrives. Large tracked excavators begin the primary excavation once the route is finalized and stabilized. They dig the trench to a precise width and depth that allows sufficient space for both pipe placement and subsequent backfilling operations. One can notice how the excavated soil is sorted immediately on site. Material that meets technical specifications is retained for later use, while unsuitable rocky or loose soil is hauled away. Maintaining a consistent depth and perfect alignment is essential to prevent the steel from deforming or misaligning after it is buried. But what happens when the pipeline encounters steep and rugged mountain terrain? It seems simple to follow the Earth's contours, but solid rock requires a different approach. Engineers use explosives to carve trenches directly into the bedrock by placing controlled charges in a calculated sequence. The detonation fractures the stone along the planned alignment with millisecond precision. This creates a trench of sufficient depth and width to seat the pipeline securely where mechanical digging is physically impossible. Transition to the next level. Pipe sections are never placed directly onto the raw trench floor after the excavation is complete. A layer of selected material, usually consisting of fine-screened soil or sand, is spread evenly along the bottom to create a bedding layer. This specialized base distributes the weight of the steel uniformly and prevents stress concentrations that could damage the structure. The bedding is leveled and lightly compacted until it reaches the required elevation. In loose desert soils, this step is the only way to ensure the long-term stability of the entire system. 18 meters is the standard length of the pipe sections selected for this project to minimize the total number of field welds. These massive components impose extreme demands on lifting and transportation systems during the alignment phase. At the welding site, a hydraulic internal line-up clamp is inserted into the joint. One can notice the 360-degree gripping shoes expanding to hold the two sections perfectly concentric. This keeps the steel aligned during the critical root pass of the weld. It gets more complex further on. An automated welding operation, supported by a workforce of approximately 80 specialized personnel, moves along the line. This mobile factory utilizes dozens of machines to complete up to 150 welds every day on 42-inch diameter pipes. Every single joint undergoes an automated ultrasonic inspection to detect any internal defects or microscopic cracks. Once cleared, a coating crew performs abrasive blasting to clean the steel surface. They then apply a multi-component liquid epoxy that forms a durable and fully sealed protective layer. The assembled pipe string is lowered into the trench using side crane tractors, which are specialized tracked vehicles designed for heavy lifting. Multiple side booms operate in a synchronized sequence, lifting the heavy steel with padded slings and cables to protect the new coating. The equipment gradually raises the pipe string and holds it suspended as the machines crawl slowly forward. Precise coordination between the crane operators is mandatory to prevent any twisting or contact with the trench walls. One can notice the pipe descending centimeter by centimeter until it rests at the center of the trench on the prepared bedding. Surveyors continuously monitor the elevation and natural curvature of the pipe during the lowering process to ensure no residual stresses are introduced into the metal. This controlled method is ideal for the long, straight sections of the route crossing the flat desert. After the pipe is positioned, the trench is backfilled in multiple layers. The first layer consists of fine material meant to shield the coating from abrasion. The previously excavated soil follows as the secondary fill. Each layer of soil is mechanically compacted to achieve the specific density required by the engineering specifications. This minimizes future settlement of the ground, which could lead to pipe movement. In conditions where the soil structure is constantly challenged by wind and temperature extremes, This compaction is the final safeguard for the pipeline. The material is covered, and the desert surface is restored to a stable state. Thus, the steel reaches the standard ready for the further stage of the project. 1,000 meters offshore is the typical distance where the process begins by drawing seawater directly from the open ocean and channeling it inland. Why is it necessary to establish such a lengthy intake route far from the shoreline? It would seem simpler to draw water from the shallow surf, but in reality, deeper sources provide a steady and uninterrupted supply of raw water with lower concentrations of organic debris for the desalination facility. This distance ensures that the intake remains unaffected by coastal sediment or surface fluctuations. The process is only gaining momentum. Large intake lines are first positioned offshore, where installation crews carefully align each section before lowering it into place with heavy lift cranes operating from barges or coastal platforms. One can notice how the crane arms move with deliberate slowness as they counteract the swaying of the ocean currents. As the pipeline extends toward the shoreline, individual segments are connected sequentially, forming a continuous conduit designed to operate under constant hydraulic load. These pipes, often several meters in diameter, represent the primary artery of the entire system. Everything only gets more complicated. Precision alignment is critical at this stage, as even minor deviations can affect long-term performance and flow efficiency across several decades of operation. One can notice the camera glides along the joints, where specialized divers and automated sensors confirm the seal of every connection. It only looks obvious to lay pipe on the ocean floor, but in reality, the underwater topography requires constant monitoring to prevent stress points on the material. Once assembly is complete, the intake line is reinforced with structural support frames and securely anchored to the seabed to withstand the relentless force of tides. The heavy steel frames sink into the sand, locking the conduit into a permanent position. But this is just the beginning. The infrastructure is now ready to transport millions of gallons of salt water toward the inland treatment basins. From here, the transformation moves to the next phase of processing as the raw water enters the filtration sequence. 63 centimeters. This is the diameter of the intake pipes that initiate the complex journey of seawater into the heart of the desalination plant. Through these massive steel arteries, up to 15 million liters are drawn every single day, translating to a relentless flow of more than 10,000 liters every 60 seconds. The process begins with the physical displacement of liquid from a point located several hundred meters away from the shoreline, where the intake occurs far from the volatile coastal waves. Why is the water drawn from such a specific distance offshore? At first glance, the ocean seems like a uniform source of raw material, but in reality, drawing water from deep offshore zones ensures a more stable temperature and mineral profile while avoiding the heavy silt found at the tide line. Barrier systems and heavy intake filters are positioned here to intercept large floating debris and protect marine life from being pulled into the mechanical infrastructure. Powerful centrifugal pumps generate the necessary vacuum to pull the seawater toward the inland facility. One can notice how uninvited biological guests, such as jellyfish, crabs, and small fish, are occasionally drawn into the stream along with the water. To protect the delicate internal machinery, the plant utilizes a massive primary screen designed to block any object larger than 4.5 millimeters in diameter. The process is only gaining momentum. After the initial barrier, the flow transitions through a series of increasingly finer screens to capture any remaining large-scale organic particles. Even when the larger organisms are successfully diverted, the liquid remains saturated with suspended sediment that obscures its clarity. Everything only gets more complicated as the water moves into the filtration tanks. Gravity drives the liquid downward through thick, dense layers of specialized sand. The spaces between these individual sand grains are so microscopic that they function as a physical sieve, allowing water molecules to pass while trapping suspended solids within the jagged edges of the minerals. One can notice how the sand itself is in a state of continuous downward motion, moving in the opposite direction of the rising or falling water to ensure the filtration media remains active. Dirty particles cling to the surface of the sand grains through friction and adhesion. It seems simple to filter water through sand, but in reality, this stage must remove every particle larger than approximately 1/10 the thickness of a human hair. The plant then introduces two critical chemical agents: sodium hypochlorite, which acts as a disinfectant, and ferric chloride, which serves as a coagulant. Large mechanical paddles stir the mixture with a steady, rhythmic rotation to ensure even distribution throughout the volume. This causes fine sand and waste particles to cluster together into larger, heavier masses known as flocks. These flocks gradually settle to the bottom of the sedimentation tanks due to their increased weight. Most of the visible dirt has been stripped away at this point, but the water is still far from the purity required for the next technological phase. Transition to the next level occurs at the cartridge filtration station. This system represents the final physical defense before the water reaches the high-pressure membranes. Multiple cartridges, constructed from tightly compressed fiber layers, are housed within reinforced steel cylinders. These fibers have pore sizes ranging from only 1 to 5 microns in width. As the seawater is forced from the outer shell toward the center of each cartridge, microscopic debris becomes entangled within the fiber matrix. Once a single cartridge becomes saturated with trapped particles, engineers must manually remove and replace the component to maintain peak hydraulic efficiency. The water that exits this stage is visually clear, yet it remains chemically identical to the ocean. Why is salt so difficult to strip from the water at a molecular level? The challenge lies in the fact that salt ions are bound to water molecules through intense electrostatic attraction. To break this fundamental chemical bond, the facility must apply massive physical force through a process known as reverse osmosis. High-powered centrifugal pumps are engaged to generate a pressure that exceeds the natural osmotic balance of the liquid. The equipment gradually increases the force through successive compression phases, where each stage of the pump assembly builds upon the last. One can notice the hum of the motors as the pressure reaches 60 bar, which is 60 times the weight of the Earth's atmosphere. This extreme force pushes the water through an ultrafine reverse osmosis membrane, while the salt and impurities are left behind as a concentrated brine. After this first round of high-pressure filtration, the water is nearly salt-free, but it still contains trace ions that must be eliminated to meet strict industrial standards. But this is just the beginning of the purification. The water is immediately directed into a second stage of reverse osmosis. Here, even finer membranes are utilized under a lower pressure setting to achieve a higher degree of salt removal efficiency. This secondary pass strips the remaining ions and reduces the electrical conductivity of the liquid to near zero levels. The result is a stream of ultra-clean water characterized by near-perfect purity. However, this water is currently too acidic and too pure for human consumption or agricultural use. The plant must now adjust the pH level by introducing a calculated amount of acid or a balancing solution to bring the liquid back into a safe neutral range. Because the desalination process removes virtually all minerals, the water lacks the essential elements found in natural springs. To correct this, small quantities of calcium and magnesium are reintroduced during the remineralization stage. This step increases the alkalinity and restores the natural taste that consumers expect from high-quality drinking water. From here, the finished product enters a modern pipeline network designed to serve the residential areas across Saudi Arabia. While the engineering is a triumph of modern physics, the financial cost remains significant. Producing 1 cubic meter of water here requires approximately $5, a sharp contrast to the United States, where the same volume might cost only a few tens of cents. Thus, the steel and salt transformation concludes as the water begins its final distribution.